So let's go ahead and see an example of a function and see why this is called spherical coordinates. Let's say that I have a sphere, and the sphere has radius 3. We're just going to go back to similar to our cylinder example. Well, if I were to describe this sphere, I can do it two ways, just like we did it 2 ways before. One way is to visually evaluate the points on this sphere. So we see that for any given point on this sphere, here's my point, I'm going out. How far is my distance out? My rho in this case is always going to be exactly equal to 3, because no matter what point I pick on this sphere, the distance from the origin is always going to be exactly equal to 3. What angles can it make with the z-axis? As the points go down, I really want to be able to trace out all of the points along all the way from where the angle with the z-axis is 0, all the way until I get down to the bottom of this circle. And so that means that my phi values, so I'll say that my rho is equal to 3. My phi values should be going between 0 and pi. And the reason why I only want to go to pi and I don't want to trace backwards is that if I go past pi, pi is where I'm making the angle with the z-axis that's exactly negative facing. My theta takes care of going around in a full circle. So in this case, my thetas are going to go, this is my x-axis, theta is going to spin all the way around in a full circle, and for each of those full circles, my phi is tracing out all of the positive and negative values. So, this is my sphere. I would say that my rho is exactly equal to 3, and my thetas are actually unrestricted, because these are the natural bounds on phis and thetas, that essentially I can go in whatever angle direction I want. I want to be able to trace out all those angles, just making sure that my radius is exactly equal to 3. And that's one way to describe this. Another way would be algebraically. Algebraically, I could say, aha, I know the formula for a sphere. This is saying that x squared, that's a squared, plus y squared plus z squared is equal to 3. And I know what z squared is. It's all this stuff squared. I know what y squared is. It's all this stuff squared. And I know what x squared is. It's all this stuff squared. And I can do all of that, 3 squared. I can do all of that computation, which I'm not going to do, which you could do. You could plug in each of these things for each of these things and simplify it. You're going to get sine squareds and cosine squareds all over the place, and they're going to start canceling, and you'll end up with exactly what we found before, which is the fact that my rho has to be equal to, my rho squared will end up being equal to 3 squared, which means that rho will be equal to 3, because we tend to only restrict ourselves so that our distances from the origin are positive. We don't think of them as being negative. So I'm going to talk really briefly about integration of polar coordinates, because it's going to be exactly analogous to what we see with triple integration in cylindrical coordinates, So when looking at integration in polar coordinates, let's say I have a double integral over a region R of some function in terms of x's and y's, and I'm integrating with respect to the area. And in this case, our areas were rectangles. We always use rectangles. When I convert that into polar coordinates, a lot of this is what we think that it should be. My x-coordinate is r cosine theta. My y-coordinate is r sine theta. That's what polar coordinates tell me. However, when I do this coordinate transformation, I have this extra term of integration. It's this r, red r. And I'll show you an example of how you use this computationally. I'm going to talk briefly about the theory of why we need to add this extra r, this term of integration, when you convert to polar coordinates. If you want a more complete explanation, I'm going to post an optional video that goes over some theory that I don't expect you to master or even necessarily know. But for your own educational interest, you could learn some of the theory behind why coordinate transformations require these extra terms. So the short answer is that when I'm looking at this in terms of polar coordinates, typically, so I have some region, this is my region, and before, when we were talking about regions, we estimated them by tiny triangles. Now, instead of tiny triangles, our slices are actually going to be these tiny little segments of circles. And so maybe I'll highlight this in red. This red tiny segment here is going to be given by a change in my theta angle. As I sweep from here to here, my theta angle is changing, and a change in radius. As I go from here to here, the radius value is also changing. So my d theta dr can no longer be approximated by rectangles. I'm actually approximating it by these tiny slices of circles. And algebraically, it means that this little tiny slice, if I called it delta A, I'll return to black so that you can see it better. It's actually dependent upon how far out I am in my radius. You can see visually, I'm not going to go into much theory. You can see visually that down here, a change in R is going to have a tiny little effect on the change in the total area. Whereas as my R changes, it'll have a bigger and bigger effect on the change in area. So this little delta A is actually a function of how close I am to the origin, meaning as I radiate outwards, this R factor is going to change what the area of each of these little differentials. And this here is the measure of that area of my differential. And so in order to accommodate for the fact that as I go outwards, my differential is going to change in area, that's taken care of by this R term. That's all the theory I'm going to say here. If you want to see more theory, it actually comes with no matter what coordinate transformation we use. Whenever we transfer, it means that we're smushing or squishing what our little delta rectangles might look like, and that change in area is given by some term of integration here that we call, well, it's the determinant of the Jacobian function, depending upon what type of coordinate transformation you're undergoing. More details in the other video. So in this example, consider an integration problem. It's a double integral over some region R. My function is x plus y, and I want to integrate this where my region R is given by this crazy shape. This has an inner circle of radius 1 and an outer circle of radius 2. Now, one way to compute this would be to set up the region of integration in terms of x's and y's. I'm going to say, that's a lot of work. That's difficult because these circles have really difficult bounds, and it makes this integration problem really hard. So instead, we're going to convert to polar. Because in polar coordinates, it's much easier to come up with the bounds of integration. So first, I'm going to look at my bounds of integration, and I say, what is my theta doing? My theta is changing from theta equals 0 all the way up. I'm tracing out the values until theta equals pi over 2. So 0 is less than or equal to theta is less than or equal to pi over 2. And then my radius in this case is shifting from a radius of 1 out to a radius of 2. So 1 is less than or equal to r is less than or equal to 2. So now I have my bounds of integration. The last thing that I need to do is set up my integral. So looking at this integral, I know that theta is going from 0 to pi over 2. I know that r is going from 1 to 2. And I have to convert my x plus y into what I actually want. X is equal to r cosine theta, and y is equal to r sine theta. But, cautionary tale, because I converted to polar coordinates, I need to remember my red r. And so my red r is multiplied by my function, dr d theta. So now that I've set up my integration, all I have to do is solve this integration problem. So erasing this, I'll erase all this stuff. We don't actually need any of this to compute this integration. So I'm going to step over here and simplify this integration problem. My thetas in this case are going from 0 to pi over 2. My r's are going from 1 to 2. I'm looking at this function. I'm going to multiply through my r's, and I get r squared cosine theta plus r squared sine theta dr d theta. Notice that the order of integration is actually arbitrary, just like Fubini's law tells us, because neither of the bounds are functions of the other variable. I could interchange this order of integration if I felt like it. I'm going to leave it the way that it's written right now, because now I take my integral with respect to r. Actually, I could even, let's factor out our r, and we're going to get r squared times cosine theta plus sine theta dr d theta. Again, this is the double integral. And notice, now I actually have a product of a function of two variables. Let's revisit a technique that we saw all the way back in 15.1. I'm going to do a separation of variable technique, because this is just a function of r and this is just a function of theta, and they're multiplied by one another. I'm going to set this up as the integral is r equals 1 to 2 of r squared dr multiplied by the integral of the function of theta. So in this case, theta is going from 0 to pi over 2 of cosine of theta plus sine of theta d theta. I don't know if this is actually faster, but it's a nice application of some of the theory that we've seen previously. It does mean that it's easy to integrate these pieces. So integrating r squared becomes 1/3 r cubed evaluated from r equals 1 to 2. That becomes 2 cubed, which is 2, 4, 8/3, minus 1/3, which is 7/3. Again, this notation is terrible. And that's what I get for this chunk. This chunk over here, when I integrate with respect to theta, the integral of cosine is sine, so I end up with sine theta. The integral of sine is negative cosine, and I evaluate that from theta equals 0 to pi over 2. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. So I get 1 minus 0 when I evaluate at pi over 2. And then I'm going to subtract out the sine of 0 is 0, minus the cosine of 0, which is 1. And so I have 1 minus negative 1, which is 2. So multiplying these two together, I get that my final integral is equal to 7/3 times 2, which is 14/3. Except in the fact that hopefully my algebra was done correctly.